The following is a special lecture titled, Your Universal Insignificance. The lecturer is Professor David Helfand. Professor Helfand is a professor of astronomy and chair of the department at Columbia University, where he has been teaching for over 25 years. He received his BA from Amherst College and went on to earn his master's in physics and PhD in astronomy from the University of Massachusetts. In addition to his teaching duties, Dr. Helfand is also the co-director of the Columbia Astrophysics Laboratory and has held visiting positions at Cambridge University, the University of California at Berkeley, and the American Astronomical Society. He is the recipient of several awards and honors, which include the Great Teacher Award from the Society of Columbia Graduates, the Columbia University Presidential Great Teacher Award, and the Distinguished Graduate Student Teaching Award, as well as the Porter Prize in Astronomy.
I'm David Helfand, chair of the Department of Astronomy and director of the Astrophysics Laboratory at Columbia University, and I am totally and utterly insignificant. I'm made of a trace constituent of the universe. I'm smaller than a speck of dust on the sea of space-time, and I'm going to be gone in the blink of an eye, blind to most of what the cosmos conveys to me. I'm going to spend the next 30 minutes trying to convince you you're no better off than I am. What's in this picture? And where are you in this image of the sky? This is a question that has consumed humanity since the first sentient hominid looked up at the nighttime sky. These ancestors of ours on the plains of the Serengeti didn't, of course, have the spectacular views provided of the cosmos by the Hubble Space Telescope, but one knows they must have wondered, what are the 1,000 points of light that twinkle in each nighttime sky and remain fixed in location compared to each other for an entire human lifetime? And what distinguishes them from the 6 other little points of light that wander around amongst that fixed field of stars? How far away are they? When were they made? What are they made of? For 99.9% of the time that our species, Homo sapiens, has walked on the Earth, we haven't had a clue. But now we do. We live at a unique moment in the 4.5 billion year history of Earth when a collection of earthly atoms have come together in a form that recognizes its place in the universe. And the news is not totally good. We are completely, utterly, and fundamentally insignificant. The process by which we've come to this view is science. Built on the foundations of Greek natural philosophy and Arabic mathematics, science in its modern form emerged in the Renaissance as a completely original and profoundly powerful way of examining the physical universe. And as a consequence, it has allowed us to gain a perspective on that universe and, perhaps more importantly, our place in it. Ted Harrison, in his elegant book Cosmology, The Science of the Universe, where he notes that the word universe comes from unity of the diverse, divides the thinking of humankind into 3 major periods concerning its place in the cosmos. He calls them the anthropomorphic, the anthropocentric, and the anthropometric view. The anthropomorphic view is an age of magic. It's when the forces of nature are manifestations of human emotions, and there's no division between the self and what lies outside it. Some of this remains in our language today. We talk about angry storms and gentle breezes as though they had human emotions. Indeed, we imagine this is what prehistoric times were like, but one could argue that the anthropomorphic view of the universe still maintains sway in the world today, and there are pockets of it, like California, for example. The anthropocentric universe is the age of myth. We create in this universe a pantheon of powerful gods, and they control the forces of nature, but these gods are invested with human emotions and are obsessed by human concerns. The anthropocentric universe is, in a fundamental sense, an Earth-centered universe, and is indeed, if unconsciously, the view that most people hold of their place in the universe today. The anthropometric universe, on the other hand, is the age of science. It's not, as Protagoras would have it, that man is the measure of all things, but that we can take its measure. We can take the measure of things outside ourselves. The anthropometric view of the universe came into being with the Copernican revolution, which removed the Earth from the center of everything and, unfortunately, replaced it with the sun. And it is the age in which we can place ourselves in the context of the universe as a whole. And so I'm going to begin this process by trying to give you a sense of the scales of space that science explores. What is the smallest thing that you can directly, viscerally perceive or feel? Well, I don't have very many of these left, but I'm willing to sacrifice one of the hangers-on for you. Oh dear, I got two. That's very bad. Anyway, this is a human hair. Take your hair and hold it at arm's length. It's pretty small. You can barely see it. You need pretty good light. If you had someone else take it and move it 3 times farther away, it would disappear. It would be below the limit of your vision. Now, that's equivalently to taking the hair and slicing it in thirds lengthwise, but it's a little easier just to move it away. So 1/3 the width of a human hair is the limit of what you can see. That turns out to be about 1/100th of an inch. Now, that's the small scale. What about the big scale? What's the largest distance that you can directly perceive? Well, you can say, I'll get on a plane and I'll fly to California, and I know I've gone 2,500 miles, but you don't have any sense of actually moving, and you don't really have a visceral feeling for what 2,500 miles is. I mean, indeed, you could sit on the runway waiting for the de-icing machine for 3 hours, and it's just as uncomfortable as flying to California, and you haven't gone anywhere. Cars and trains aren't much better because you, again, don't have an actual physical sense of the distance you're covering. The odometer is not the same as your legs. So take a week and hike the Appalachian Trail. If you didn't sleep too much and you're in pretty good shape, you could probably go 100 miles. Or if you're a bicyclist, maybe if you've, in really good shape, done a century, which means you do 100 miles in a day. I would submit 100 miles is about the maximum distance that the human body can directly experience. So I've got 100 miles, that's the distance from New York to Philadelphia, and we've got my hair on the other end. What is the ratio of those distances? In other words, how many hairs would I have to lay down on the road to Philadelphia side by side to cover up that road? The ratio of 100 miles to 1/100th of an inch is a factor of 1 billion. Now, 1 billion is a big number. If I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, I can do that in about 5 seconds. So if I kept that up 8 hours a day, and I didn't take weekends off, so I did it 7 days a week, I would get to 1 billion in about 28 years. It takes a lot of hairs to cover the road from New York to Philadelphia. That's a huge range of scales that we're used to exploring. But what is this hair made of? It's made of atoms. And if I go smaller than this hair by a factor of 1 billion times narrower than this strand of hair, I'm still on a scale that's too large to explore the structure of the nucleus that anchors each of the atoms in the hair. And if I go 1 billion times farther from New York to Philadelphia, that is, I do it 1 billion times, I get a distance that's barely outside the edge of the solar system. And if I go another factor of 1 billion beyond that, beyond the edge of the solar system, I'm still trolling around in the local universe. Indeed, the total range of scales that we explore, from the size of the quark inside a proton to the dimensions of the universe that I can observe from Earth, it's about a factor of 100,000 billion, 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 billion. That is, if I lined up quarks from one edge of the universe to the other, I'd need 1 followed by 41 zeros of them. That's rather a difficult concept to get your head around, 1 number followed by 41 zeros. And so I've got a few analogies for you. So I saved my orange from lunch here. Here's my orange. And we're going to start off with the small scale, the atoms that make up the hair. You've all seen this in a high school chemistry book, no doubt, that here's the orange, it's the nucleus of the atom, and then drawn in the textbook were little electrons orbiting around like planets around the sun. Well, that, of course, is actually a nonsense view of what the atom is. If this orange represents the size of the nucleus, then the first electron orbit is a half a kilometer away across the street in another parking lot. The first one. Meaning the atom is 99.999999999% empty space. Which is pretty remarkable, because it means my hand, which is made up of atoms of 99.999999999% empty space, and this table, which is made up of atoms, which are 99.9999999% empty space, you'd think would be able to just pass through each other, but clearly they don't. That's because of the forces that hold the particles together are really rather strong. Atoms this large, where the chalk is in the parking lot and this represents the nucleus, so on a scale that I can see what's going on inside the core of the atom, would make a hair 1 million miles wide, or 5 times the distance to the moon. If I compress the atom down, so the whole atom fits inside this orange, and then I've got orange, orange, orange atom making up the hair, the atoms all touching each other, the nucleus would then be infinitesimally small. I couldn't see it inside at all. It would be a tiny little speck that I couldn't see. And then the hair would only be as wide as New Jersey. So atoms, the small scale, are very, very small and very remote from the scales that we can experience directly, the smallest of which is my hair. Now let's go to the other scale, the large scale of the universe. So we'll now transform the orange. It's now become the sun. So here's the sun. It sits right there. In reality, it's about 1 million miles across, but we've squished it down so it's the size of the orange. On that scale, the Earth is represented by this fleck of chalk dust, which resides at a distance of something like that and orbits around in a period of a year. Jupiter, the largest of the planets, is about that big, and it would be way over there in the end of the room. Neptune, the most distant planet, would be out in the parking lot outside the building here. And then the next star, which is a star very similar in size and color to the sun, so it would be good to represent it as another orange. If we're here in Washington, D.C., the next star, the next orange, would be in Minneapolis, and there's nothing in between. Then there's another orange that's in Los Angeles, maybe a grapefruit in Honolulu, and a plum in Singapore, and about 100 billion pieces of fruit scattered around in a great spiral disk that we call the Milky Way. In 1900, we thought that our sun, which Copernicus had put at the center of the universe, lay at the center of this spiraling disk of stars, the Milky Way. But then we learned that indeed we're really out in the boondocks somewhere, pretty far from the center at all. Then, in 1930, we thought that our Milky Way was the universe. The 100 billion pieces of fruit scattered around at great distances made up the universe. But we learned then that indeed it's not. Our galaxy, our 100 billion stars, represents just one tiny little island in a universe with at least 100 billion galaxies that we can see, and a universe that has no center at all. So, on the scale of things in space, we are totally insignificant. Now, I left unanswered in that little peroration something that perhaps the more curious among you would have wondered, and that is why? Why is this hair, the thickness that it is, the limit of human vision? Well, curiously, that's a consequence of 2 numbers that at first blush would have nothing to do with the physics of vision: the temperature of the surface of the sun and the gravity, strength of gravity on the surface of the Earth. Those are the 2 numbers that set the limit of human vision at the width of a human hair. Well, how can this be? How can I connect those things? Well, first we better understand what we mean by vision. Vision is a process, unlike you see in the cartoons where little beams come out of people's eyes, that's completely passive. You see me standing here because light comes from these lights here, bounces off me in just such a way that it travels directly into your little tiny pupil, the black spot in the center of your eye, is focused by the lens, is absorbed by tissue on the back of the eye called the retina, where it's transformed from light into an electrical pulse, which goes to this region of the brain back here and produces an image of me before you. Well, all right, sounds like we have to step back one step further and ask, what is this light? Light, to a physicist, is a self-reinforcing electromagnetic wave that propagates through space at the remarkable speed of 186,000 miles per second. What do I mean by that? The basic laws of electromagnetism were understood in the middle of the 19th century by James Clerk Maxwell. And he wrote down 4 very simple relations between electricity and magnetism, which up until that time had thought to have been separate forces. But indeed he showed that if you change an electric field, you get an electric force gets bigger, then a magnetic field is magically created. And if you change a magnetic field, make it bigger or smaller, an electric field is produced in turn. For light, we have these 2 fields perpendicular to each other, such that as the wave of light or the wave of electric field gets bigger, the magnetic field gets bigger, and then as it gets smaller again, the magnetic field gets smaller, and this wave propagates like this in a self-reinforcing manner, so it never loses energy and moves through space at this remarkable speed. So what happens then is that these lights are producing these waves that come instantaneously, as far as I can tell, bounce off me and into your eyes. What makes the rich, variegated world that you see around you? All the waves of light travel at the same speed. The only thing that distinguishes them is their wavelength. That is the distance between the crests of the wave as it travels by. In the case of our eye, red is the longest wavelength that the eye can measure. The eye represents wavelength, or the brain represents wavelength as color. Violet, purple, violet, is the shortest wavelength we can measure. And the distance between them is just about a factor of 2. That is, red waves are just about twice as long as violet waves. A factor of 2 in sound is an octave. So we can say that the eye sees a single octave out of the rainbow of colors that are produced by electromagnetic radiation. What about if we went to waves a factor of 2 longer? Well, if you've been to a hotel that has a heat lamp in the bathroom, you can detect those waves with your skin. You feel warm, but you don't detect them with your eye. The light may emit a little visible red light that your eye can see, but most of its energy is coming out in a region of the spectrum to which you are completely blind, and you can feel the heat on your skin. What about a factor of 2 shorter in wavelength, a factor of 2 shorter than the violet? Well, that moves us to the ultraviolet part of the spectrum, and if you're so foolish enough as to do so, your skin can also absorb those kinds of energy and rearrange your molecules, sometimes to not very good effect, if you put yourself under a tanning lamp. But you can't see those rays because they're absorbed in the cornea of your eye and they never get to the place where a signal is transmitted to the brain. Indeed, the spectrum is much, much broader still. If I go down a factor of 100 in wavelength, I come to the microwave part of the spectrum. If I go up to a factor of 100, I go to the X-ray part of the spectrum. Electromagnetic waves can have any range of wavelengths we want. And from radio waves and TV signals to the microwaves in your microwave oven to all infrared radiation, the full spectrum of colors of the rainbow, which is just a single octave, the ultraviolet light, X-rays that the dentist uses on you, and gamma rays span at least 50 octaves of the spectrum. And your eyes see just one. It's really pretty pathetic. Your ears can hear 10 octaves, from the low notes on the piano to the high notes on the piano and perhaps a little above. You can hear 10 octaves of sound simultaneously. Imagine what it would be like if you're listening to a Beethoven symphony and you could only hear a single octave at a time, just the A above middle C to the A above that. That's all you could hear. No basses, no piccolos, just that single octave. That's how blind we are to the universe. In fact, we're even more blind because we're seeing 1 out of 50 octaves, not just 1 out of 10. And so my second point was that I'm blind to most of the signals that the cosmos conveys to me because I can only see in this single octave of the spectrum. Now, that doesn't get back to my original contention that the eye is seeing these small distances in this narrow spectrum because of the temperature of the sun and earth. How does that work? Temperature is just a measure of the speed with which atoms or molecules that make up a substance are moving. In the air in this room, the molecules are moving around at about 450 meters per second. That is, if they didn't collide with each other, they go back and forth across the room 30 times a second or so. But they do collide with each other, rather like billiard balls. They're constantly bouncing off each other, and so they don't travel in a straight line. But they're moving pretty fast, and the temperature sensation I get from being in this room is the consequence of those molecules pounding into my skin. If we turn up the heat, they move faster, they hit my skin harder, and I feel warmer. If we turn on the air conditioning, that slows all the molecules down and they move more slowly. On the surface of the sun, the temperature is 5,800 degrees. That means the molecules even move much faster, of course, than they do in this room. And the molecules, as they move by each other on the surface of the sun, emit waves. The faster they're moving, the shorter the wavelength, because they interact with each other for a short period of time. The slower they're moving, the longer their wavelength. Now, these atoms in the sun are not moving all exactly the same speed. It's like on a billiard table, you break the balls. Some of the balls go flying all around the table, and some of them are just rolling around slowly. The same is true of the air in this room, and the same is true of the surface of the sun. The molecules are all moving at different speeds. There's a whole range of speeds, but the majority of them, for a temperature of 5,800 degrees, are moving with such speed that they emit mostly yellow and green light right in the middle of the range of the octave that our eyes are most sensitive to. And this, of course, is not an accident. The eye has been evolving for 400 million years. And over that time, organisms have, for the most part, had 3 goals. 1, to avoid being eaten. 2, to find things to eat. And 3, to find ways to reproduce. And so it's helpful in such an environment with such a set of goals to have lots of radiation around that bounces off things and comes to your receptor and tells you, there's a predator, better hide, there's some prey, time for lunch, there's, well, we won't talk about the reproduction part, but anyway. So a mate, good. That's the temperature of the surface of the sun, matching perfectly to the spectrum of our eye. The strength of gravity on the surface of Earth is relevant as well, because that determines what kind of atmosphere our planet has. Venus, our sister planet, very similar otherwise to the Earth, has an atmosphere that's so thick and layered with clouds that none of the light from the sun gets through. So it would be useless to evolve an organism with an eye on the surface of Venus that was sensitive to our wavelengths. Our atmosphere is made of mostly nitrogen and oxygen. The reason is because of the strength of gravity on Earth. Initially, our atmosphere was mostly hydrogen and helium, as is the sun and most other things in the universe. But our gravity wasn't strong enough to hold those light atoms, which tend to move faster. Imagine again the billiard table, and this time you've got a bowling ball and a bunch of billiard balls and a bunch of ping pong balls. If you break in that circumstance, the bowling ball will barely move, the middle-sized balls, the pool balls, will move around fairly rapidly, and the ping pong balls will go flying off the table. Well, the same thing happens to the atmosphere on Earth. The ping pong balls, the hydrogen and helium, the light elements, go flying away and get lost to the atmosphere, whereas the atmosphere of the Earth retains nitrogen and oxygen, which happen to be transparent in exactly that same octave of the spectrum. So, ultraviolet light gets blocked by the atmosphere. X-rays get blocked by the atmosphere. Infrared light gets blocked by the atmosphere. Only the colors of the rainbow, which our eyes can see and have adapted over hundreds of millions of years of evolution to be tuned to, are the light that comes through. So it's very convenient. Our sun puts out the right set of wavelengths, the atmosphere transmits them, and the eye automatically comes to see them. But it's 1 octave out of 50. Most of the rest of the universe is not 5,800 degrees. Some of it's 2 degrees, and some of it's 1 billion degrees, and we don't see any of that radiation. So again, from our perspective, we're blind to most of what the universe is sending of us, at least 98%. Just as our sense of scale makes us seem so small, and our senses make us seem blind to so much of what's going on, our sense of time is also something that we have trouble comprehending. We know the history of the universe. It's written for us in a book that we just need to open and turn the pages of. Why? Because of the finite speed of light. I said earlier that light travels at 186,000 miles a second, and it's therefore essentially instantaneous when it's coming from this light bulb and bouncing off me and into your eye. But it's not instantaneous because it's a finite speed. It goes around the Earth at the equator 7 times in a second, but to the moon it takes 1 second and 1/3. To the sun it takes 8 minutes. So we see the sun when we look at it in the sky, not as it is right now, but as it was 8 minutes ago. Now the sun doesn't change that much on a time scale of 8 minutes, so not to worry. When we look at Mars in the sky, we see as it was 20 minutes ago. And this is not a problem for looking at Mars, but if you are the controller of one of those little rovers that runs around on the surface of Mars, you immediately see that you have a problem. Because the rover starts off, it's got its little camera in its head, and it's looking ahead and saying, oh look, there's the edge of a crater we're about to go over. And you in the control room in Pasadena go, oh, better stop the rover. But of course, it was 20 minutes ago that the rover was near the edge of the crater it was about to go over, and it took 20 minutes for the light to get to you. And then it took 20 minutes for your signal to say, better stop, rover, to go back to the rover. 40 minutes later, the rover is going to be off the edge in the bottom of the cliff. And that's why they move really slowly, because of this long time delay. When we get outside the solar system, the consequences really start to get interesting. The center of our galaxy is 25,000 light years away. That means it took 25,000 years for the light to get to us today from the center of the galaxy, and we see it as it was 25,000 years ago. And we believe it's different today. When we go out to galaxies near us, we're millions or hundreds of millions or even billions of light years away. We're seeing back billions of years in time. And so if we want to know what the universe looked like 1 billion years ago, we just open the page with our telescope and look back to a galaxy 1 billion light years away. If we want to know what the universe was like 10 billion years ago, we open to a different page, look at galaxies that are 10 billion light years away. And over the last couple of decades, we've managed to write the story with very fine precision, such that we know the universe began in the Big Bang a time 13.75, and we know it to that many significant figures, 13.75 billion years ago. Now, how are we going to make this relevant to human timescales? We'll use an analogy again. What's the longest range of time that you can actually directly experience? Well, of course, your lifetime is the upper limit to what you can experience, but I suspect you don't remember what happened in the first 5 years very much, and if you're like me, a lot of the years in between are a little fuzzy too. So let's pick a period of time that's a year. I mean, everyone has a good sense of what a year is. It's a long time to wait for something that you're anticipating, but nonetheless, it's a finite time. You know what you were doing a year ago, not precisely perhaps, but you know what job you were in, you know what house you were living in. So a year is a time. Let's compress the history of the universe from the beginning to today into a time span of just 1 year. And so what do we see? It's January 1st. It's New Year's Eve. It's Times Square. And the ball has hit the bottom. The crowd has cheered. And the year begins. That's the beginning of the universe. And within 12/10ths of a microsecond after that, the nuclei of most of the helium and all of the deuterium atoms in the universe today were formed. 35 minutes later, time to open the next bottle of champagne, the first atoms came together as hydrogen and helium, which make up 98% of the universe, formed into the kind of atoms, the identical kinds of atoms that we have here in this room today. And gas, overall, started collapsing into lumps as the universe expanded into space-time. And about February 18th, at noontime or so, the Milky Way galaxy, our galaxy of our 100 billion stars, formed. Then stuff happened. Stars born, stars died, other stars were born out of their ashes, other stars died. And it wasn't until September 2nd, so 9 months into the year, at 6:22 in the morning, and we know that number that precisely, a little lump of matter in our neighborhood collapsed down, became a star by igniting nuclear reactions in its core and turning 600 million tons of hydrogen into helium each second. And that's been going on for 4.5 billion years, our sun. And by early in the afternoon, a few hours later, the Earth collected out of some of the detritus left over from the formation of the sun itself. In just a few weeks, by noon on September 28th, life appeared on Earth. It could have appeared before that, but that's where we have evidence that life appeared rather quickly once the Earth formed. And then it started to evolve. And on November 15th, another month later or so, we note a striking change in the composition of the Earth's atmosphere wrought by this life. That's when photosynthetic bacteria learned to use the energy of sunlight to make themselves grow, use oxygen, use carbon from the water and the earth, and pump oxygen into the atmosphere. So that was a major transformation. And a few weeks later, at 3:58, and we know it that precisely on December 16th in our year-long scale of the universe, life blossoms in what we call the Cambrian explosion, where millions of species of enormously complex organisms suddenly burst to life after the Earth has been through an ice age. Those ancient creatures that occurred in way prehistoric time, the dinosaurs, don't show up until around midnight on December 23rd. I mean, it's right before Christmas, the end of the year. Dinosaurs just showed up. And on December 29th, at 6:54 in the morning, and we know that date precisely as well, the dinosaurs and 50% of all other forms of life on Earth, plants, animals, and ocean life, were extinguished when a 10-kilometer asteroid crashed into the Yucatan Peninsula of Mexico, ignited worldwide forest fires, threw enough dust into the atmosphere to make it dark for 6 months, and the only things that were survived on land were the furry little creatures that are ancestors of us, the mammals. They appear on December 29th, when the meteor strikes. And then the mammals evolve until New Year's Eve, December 31st, 10 o'clock in the evening. Time to go to the party, and if you're going to go to Times Square, you should have been there already. That's when the first hominids, the first of our genus, appears on the surface of the Earth, like the skeleton Lucy, 3 million years ago in real time, but in the last hour and 54 minutes of our year. At 11:54, our species, Homo sapiens sapiens, appears on the plains of the Serengeti. 5 minutes to midnight. That's how long our entire species has been around. At 11:59:33, the ball has started to drop. It starts 30 seconds before midnight. 3 seconds after it starts to drop, the mile of ice that covered much of North America, and particularly New York City, where I live, started to recede as the last ice age ended. In real years, about 12,000 years ago. In our clock here on human timescales, 27 seconds before midnight. those incredibly ancient human constructions, the pyramids, have been around a grand total of 9.7 seconds. Our form of democracy, the Declaration of Independence, inaugurated 0.6 of a second before midnight. And at 11:59, 59.874 seconds, I was born. 13/100ths of a second before the ball hits the bottom, 13/100ths of a second out of a year, which is why I claim I'm a blink of an eye. And at 11:59, 59.999999913, I started this lecture. No time at all. So, in terms of space, we're infinitesimally small. In terms of our senses, we're blind to 98% of what the universe sends our way. And in terms of time, we're a blink of an eye. We've removed the Earth from the center of the universe. We've removed the sun from the center of our universe. We've removed the galaxy from the center of our universe, and indeed conclude that our universe has no center at all. But it gets worse. Because all those hundreds of billions of stars, and each of the hundreds of billions of galaxies, 10 billion trillion stars in all, and all the planets that circulate around them, and all of the creatures that evolve on those planets, are all made of atoms. And atoms are a trace constituent of the universe, making up, we believe now, some 4.5% of the universe as a whole. Most of the rest of the universe is something else. We're an afterthought. And so, we're 98% blind, made of 95% irrelevant stuff. We're tiny, and we're gone in the blink of an eye. Pretty insignificant from the anthropometric viewpoint. But what's inspiring about this is that 1 kilogram of that trace constituent of the universe can apprehend its insignificance with such striking clarity. The fact that we can use our telescopes and our Geiger counters as time machines to write the enormous history of the cosmos. The fact that we can assay the composition of the most distant galaxy and find it made of atoms identical to our own. These are the crowning intellectual achievement of our age and render our utter insignificance insignificant.